Hello, everyone. Here we talk about the phase lead controller design in the frequency uh, domain. This contains two portions. One is the first portion is about the introduction of the steps. The second portion is to use one example to demonstrate these steps. Uh, you have seen the lead controllers in the root loci. So basically, the lead controller have these features. It's pole. It has the zeros, and 0 is at minus 1 over t, and pole, for example, say for alpha equal to 0.5, then that is minus 2 over t. So that is the features of the lead controller designs. And if you draw the body plot, and basically at the lower portion here, if you draw the body plots for these functions and that has the features, this is the magnitude, and this is the phase angle. And basically the phase angle have the feature is, you can see the lead controller have a positive phase. So here we talk about the basically two features. One is to contribute a positive phase angles. Okay, the maximum is these numbers here, and we're going to formulate later. And for these demonstrations, and we demonstrate is for alpha equal to 0.1. The second feature is the lead controller basically at the high frequencies is magnitude is 0 dB. So basically contribute nothing to the original systems. Okay, so keep the figures in mind, and we're going to later to review it. So the first one, let's to based upon these generic patterns in terms of the Kc, which is gain, t, which is a parameters, and alpha, another parameters. So here in the lead controller, three parameters we're going to find. The first of all, let's find in terms of the body plots, let's define certain key features. The first one is to find out at which frequencies and what is the maximum phase angle that the controller can have. And then at that frequencies, what is the magnitude, which is here in drawing is h. Okay, so that is a formula I already put up here, and those are calculations. We can go over this one carefully. So the first one, let's answer what is the maximum phase angle here. So basically this is easy. So we given this is the angle. So basically here I forgot this should be angle. Okay, the angle of the phase lead controller is described by this. That is the angle of the numerator and minus the angle of the denominators when s equal to j omega. Okay, so that means when s equal to j omega, we put into here. And to calculate the maximum value, we simply take the derivative setting equal to 0. So from here, we can find the omega equal to this one. So here, at this corner, at this frequencies, and the omega equal to this number, we calculated here already. And then at that angle, at that frequencies, we simply calculate the angle of this controller. And then we can, after the few steps, basically is this number. Okay, so that is this number we calculated. And also, at this point, we also calculate the magnitude. Basically, the magnitude here is given by this number. Okay. And on the other side, we calculate the magnitude of this controller at a omega is very small, so that is perceived here. And so to that case, then the magnitude equal to Kc. So basically, the h simply is a difference in decibel between here and here. So we simply taking the decibel, that means 20 times log of this number minus the 20 log of this number, which means again here we calculate simply is the difference in decibel between the two levels, and that described by here, and we found that is this number. Okay, so basically in this page the formulas are described in this graph. So here we talk about is the um, when we use um, the facelift controllers. Okay, and this is the one example here for an uncontrolled open systems. So for example, here is that for this function. So here is the border plots of these functions. So for this case, you can see we have the phase margin here. The phase margin per MATLAB being calculated is about 9 degrees here. And in certain design criteria, we like to have the first margin, for example, say 50 degrees. So compared to the given 9 degrees, we're looking for 40 more degrees contributed by the controllers. So positive 40 degrees be contributed by controllers. So in this case, we're looking for phase lead controller design. Okay, so that is the case here. Um, And in this drawing, basically I show is two possible schematic placement of the controllers. For example, the first controller is in green color. So for example, that this controller has about the phase angle, the maximum is about 40 degrees. So that can be placed here. So in this way, they're going to, once you overlap and superpose the two uncontrolled figure with this one, basically you can see this frequency, which is about 8 omega equal to 8 radians per second. Then this phase angle will be about 10 degrees plus this one about 40 up to here. Okay, the second scenario is this: we can have a larger, the phase leader have a larger contribution of the angle. For example, from here to here is you can measure is about 40 degrees. 40 degree plus the original here is 5, so basically that is 45. So basically the late controllers is about how to select the size, the maximum phase angles, and also which locations you're going to place the controllers to overlap with the original and to modulate the response. Okay, so keep this in mind. So here, let me reiterate these informations here. So basically here, this is the uncontrolled systems, and here usually for the uncontrolled system and open loop systems, we have unsatisfied phase margins. So here we want to have the phase lead. For example, here we put into feed forward configurations, hopefully with the positive contribution of the phase angle from here to improve the phase angle, the phase margin of the open loop system, which here. Okay, so the goal is to increase the phase margin of closed loop system. The method that is the head up, the big pictures of the method. So here we select the lead controllers, and that has this contents. In particular, we have alpha less than 1 to be eligible phase lead controllers. So in terms of these closed loop systems, we have the characteristic equations, and we plug in the information of the GS to here. So basically, let me rewrite. Okay. So in this way, I rearrange the form. Basically, I rearrange the form. I simply the multiply alpha on the numerator and denominators, and then put into here. Okay, and then that alpha will be come to here. So basically, alpha combined with Kc, I have a Kc alpha, which is a constant. I group this with GS. And in our textbook, this is termed as gain adjusted GS or gain adjusted open system. So the design will have two big steps. One is about this. The other one is about this. Okay, we move on. From this page onward, for a few steps, then we have 5 steps, and each step for one slide. Okay, I will explain one by one. The first one, we are dealing with the this term here. The first one, we determine the Kc alpha by meeting the steady state requirement, and so we keep this one. How to do this one, and we will have one example to demonstrate. Okay, the second step is for these gained adjusted functions, we draw the body plots. And then for this, basically this is sort of the open system. We draw the body plots, and then we look into its phase margins, and usually it's too small. And then we determine the desired phase angle increase, theta. So that is a portion going to be contributed by these controllers. The next step is to determine the maximum angle. From there, we could determine alpha. Okay, so basically, this Vm maximum usually is the desired plus this range, because this is the design. So usually, this range allow us certain flexibility to do the refined modulations. Okay, so usually this number is arbitrary. You can pick whatever you like between 5 to 12 degrees. And this range is recommended by many textbooks. Okay, so for example, say theta determined is 40, you plus 45 degrees, so maximum Vm is 45. So once you have a Vm here determined, that you can proceed this one to determine alpha. Okay, so again, in these controllers, we have Kc, one parameter, alpha, the second parameter, T, the third parameters. And from the previous page, we the first step, we have the first equation being formulated, and then from here we solve for alpha. So we are needing the last equations, in total 3 equations for solving 3 unknowns, which is Kc, alpha, and T. Okay, so right now we're up to the second step. So to this step, we already know this magnitude, and from there we determine alpha. Okay. The next slide is to determine what is h, because we already determined alpha from the previous step. So from here, you simply put in your calculation, you can calculate h. Okay. So once you have the h being calculated, then you go over the body plots of the gain adjusted functions. You're looking for the frequency that we call the gained crossover frequency, and this one at which this the magnitude on the gained adjusted GS is negative. Sorry, here is negative. Okay, is negative equal to this one. So from here we determine omega CG, and this is the critical steps. And so that means from there we determine these numbers. And so once you determine these numbers, then in the final steps is we can determine T. Basically, once you have the CG determined, then this is known value, then you can solve for T. Okay, so this is our last equations. Again, we have 3 unknowns, Kc, alpha, and T. This is the third equations we formulated, which is the second equations. The second equation is this one. What is the first equation? The first equation is this one. From the steady state requirement, we have this value. Okay, so in total, we have 3 equations, 1, 2, 3. So that is the design steps, and these design steps is pretty tedious, and you should go over this carefully and think through. And then in the next portions, we're going to have the examples. Okay, let's stop at here for this moment.